So the question is about ease.
So like,
Ease program.
like this first one was 50.
Okay.
You have the results, wanted to see what your pressure came out to be and what phase it was in.
Okay.
So after I didn't have any issues with that, this was for R134A, by the way, I have R.
Okay. So you deleted out everything you set for, and you put in the information that you needed. You got a result for the first set of.
Actually, I tried to use these on a different problem, another couple problems.
Oh, okay.
So this, what's actually listed here, the set 4 is a different pressure than what this was going out for.
Okay.
I had just set 1.
That doesn't make any difference. The set number is just a note for you.
But so like whenever I had to key in like whatever my fluids was, like I had R14A, and then
You had R410A.
yeah.
Okay. Is that a problem in both here or something else? I don't think we do it with R410A.
Or I'm sorry.
Okay, that's all right.
I'm thinking.
I know R410 is a modern refrigerator.
Yes, and that's right.
I understand.
One,
Do you have these on Blackboard?
Yeah, there's an install file on Blackboard you can download and run. It's the trial version. I'm still working with Greg to get the full version installed. He told me that we will not be able to post the full version install file on Blackboard. It will be installed in the lab, so I'm sorry I tried to do it for you. But I'll probably contact the company myself directly because they will probably let me do it.
I'm gonna start over here.
Okay.
So it comes up here, so now you have your 4 sets.
Okay, so
I did, this is what I did, just delete this out.
All right.
And then here,
Change the fluid.
and so like this one, we were supposed to solve for the temperature. They gave us,
Hey guys, if you can keep it down just a little bit.
I'm pretty sure it was specific volume there.
You have a specific volume of pressure, you're saying?
We were meant to find.
I'm trying to find pressure. That's okay, no problem.
So right here, so we were meant to find temperature, and we had pressure, and did not have, we had the phase that was in. So, what I was trying to do, I was trying to go through here and change this pressure. And here where it's got all this other,
Why would you delete that? So you're trying to delete the functions. Let me explain. He's looking at an ease problem where he's given 2 pieces of information, he needs to find 2 others. So in this particular case, you're given, what was it, pressure and phase information. Okay. You don't want to delete the function that says P1 equals pressure of something. That's a function where you pass it something and it gives you back pressure. That's the thing that's going to go and get the pressure for you.
so what are we actually plugging in the information that we do have? The 400 kilopascal. We know that's our.
Oh, I'm sorry. I'm sorry. Okay, so this is something. You're right. I'm sorry. You would have to give it pressure because that's one of the givens. So you change this function to where you have it find, say, temperature. So you change this to the function temperature instead of pressure. Pass it the pressure. Pass it the quality. Okay, and if you look in the other sets, all of the sets have combinations like that, where you can see how to use the various functions. Because there's a pressure function, there's a temperature function, there's a quality, there's a specific volume function. But it has to know what fluid you're talking about and 2 other properties to get the other data that you're asking for. So don't delete all 4 sets. Look at all 4 sets, understand how they're working, and then use pieces you need.
That's a simple one, but I just.
That's a good question. That's fine, no problem. What else? Yes, sir.
I got a question about subcooled and superheated.
Subcooled and superheated question, okay?
So when I typed the information into ease for R134A, I got a temperature of 50 degrees Celsius, a pressure of 6.324 kilopascals.
You jot some of this down. You're saying you have a temperature of 50 degrees Celsius. What else do you have?
Pressure is 6.324 kilopascals. And specific volume is 4.16 cubic meters per kilogram.
4.16?
Yes, sir. And it said the quality was 100. Or maybe that's 1, I guess. Is that 1%?
It's not 100. Is this is what you have? This is the
That's what the information I got back from Ease.
Right, well, you gave it this, right? You gave it this temperature. You said temperature equals 50 degrees at some point, right? There was one of these others, I think it was specific volume, if I remember right. And then you use a pressure function and quality function to get these two back, right? So this one makes sense. This one, you're probably wondering, what the heck is that? Well, what it's saying is that this is not in the saturation region, therefore quality is undefined. But to let you know what region it's in, it gives you either positive 100 for superheated or negative 100 for subcooled. Okay?
All right, so I assume that it's so cool.
Well, since it's positive 100 is superheated.
Okay.
You just get a one.
You get a 1, that's a quality of 100%. In other words, all of the mass is in the gas phase and you have a saturated vapor. Now, if you'll notice, there's a time in one of these sets where you pass x equal 1 as a function. In other words, you told it the quality is 1. And so it simply returns that information back to you.
I guess whenever I put it, I didn't do that, I got back to 3.4 for pressure, so that's 6.4.
Okay, I don't know.
That's why I got 3.49.
there's that too. I don't know who's right and who's wrong. I mean, I can look at what I've done if you wanted to know. Let's see. What's the problem number again, please?
This is actually 23,
223?
323.
323, excuse me. Let's see. Where did I write this problem? Well, I know I worked it, but I don't see it, so I don't know what the correct number is. Do you need me to go through these and try it, or? I think it's successful. I don't think you really need it.
I mean, it just depends on if we're gonna.
The point of showing you how to use ease is so that you can use it in your project, because that's when it's really going to be handy. To use ease to solve an exam or to solve your homework, then probably not so much. But on your project, I think ease is going to be a godsend.
So maybe we can deep dive into it.
I think you should. I think you should understand what it's doing.
I guess if you don't even have the functionality yet, what it's doing for us.
So, for future reference,
Yes.
do you want 438
38.
for the PV diagram? You want us to show the PV diagram?
Yes. Yeah.
Okay.
If I've asked for it, I want it. Now, notice that I've asked for the P, or your author has asked for the PV diagram with respect to the saturation lines. Okay, so how would you do that? Well, all I'm really asking for is schematic. It doesn't have to be exact. Draw a generic PV diagram, draw a generic vapor belt. Try to say generic and vapor at the same time. And then plot points that represent states and lines that represent processes transitioning between those states that are correct relative to this. In other words, if the fluid starts out in the subcooled region, put a point over here. Okay. Anything you can label, do so. Okay. You can do it on the axis so that I understand that you know what's going on. Now, if you have a constant volume process, what kind of a line would you have on this? Constant volume, not constant pressure. Vertical line, right? So constant volume process would just be a vertical line because the volume is constant. A constant pressure process would be a horizontal line. Okay.
Something in between is that.
Exactly.
And also in the same one, just the technicality, do you want, it's asking if one half of the liquid is evaporated, is that one half volume or one half mass? Oh, it doesn't matter.
No, it does matter. It makes a big difference. If you start off, well, it depends. If you start off with something that is all liquid and half of it is evaporated, it wouldn't matter whether we're talking about volume or mass because it has the same density throughout. But what I always assume when they say half of it is evaporated, I assume they're talking about a mass basis. So that's what they mean. Because
It's all liquid anyway, so it doesn't matter.
yeah, if it's all liquid, it doesn't matter.
If, like in 53, I think you'll, might have been over, I think the.
453?
52.
52, okay.
52, it says it's like, a half liquid, half vapor. And then-
Okay, are we in chapter 4 or chapter 3?
Chapter 3.
Okay, let's go back to chapter.
What do you think, we're working ahead? Gosh.
Well, I just got a question from chapter 4, so I don't know.
You don't count.
Yeah,
Okay.
he doesn't have, he's got too much.
One's up there too.
A rigid tank with a volume of 1.8 cubic meters contains 15 kilograms of saturated liquid vapor mixture of water at 90 degrees Celsius. Now the water is slowly heated. Determine the temperature at which the liquid in the tank is completely vaporized. Also show the process on the 2D diagram with respect to saturation levels. Okay, so what's your question, John? How to start it? Okay. Well, we can look at that. How many people have completed problem 52? Anybody?
I didn't do the PV diagram, and
Okay.
I started looking at it, and I found one that sets an ease that would actually give me back what I needed, so I used ease.
Okay, we need to understand the process as well. So let's go through and look at this problem, see if we can figure out how to solve it. Basically, it says that you have a rigid tank. What does that tell you about the volume of the tank? Stays exactly the same. So from state 1 to state 2, the tank volume, V1, is equal to V2. It's 1.8 cubic meters. Okay? There are 15 kilograms, so the mass in state 1 is 15 kilograms. I'm not going to bother putting a subscript 1 on it, because if it's a rigid tank that doesn't leak, then there's 15 kilograms in state 2. What else are we told? We are told that it is a saturated liquid vapor mixture. I don't know how much of it is liquid. I don't know how much of it is vapor. It could actually be all liquid. It could actually be all vapor. Okay? Because saturation just means you're in that region. Okay? Now, what else do they say? The temperature is 90 degrees Celsius, so T1 is 90 degrees Celsius. Now the water is slowly heated. In other words, heat is transferred into the system. Okay. Determine the temperature at which the liquid in the tank is completely vaporized. So they're basically asking for T2. Now let's think about this for a minute. I'm going to try and push you into a hole so you don't fall into it on the exam. Are you ready? I'm going to keep your footing. Here we go. If there is liquid and vapor emission, which I think there is, and we're going to boil off the liquid, right? Why would the temperature change? Because, I mean, you take a pot of water, you put it on the stove, you put heat into it, it boils off, but we've already gone through a lot of discussion to prove that the water temperature that's liquid and the water temperature that's in the vapor phase is the same, it's 100 degrees Celsius. And until the boil is complete, the temperature never changes. So wouldn't the temperature here be 90 degrees? How many people want to bite on that one and go for it? I've already warned you this is false debate, right? So of course you're not going to. There's no way, because think about it. Now how is it possible for the temperature to change? Because I thought temperatures were constant during boiling. No, that's not necessarily the case. Yeah, go ahead. What do you think? Pressure, will the pressure increase or decrease or stay the same?
Increase.
It will increase, I agree. Why is there anything that stays constant during boiling? Because remember that during a boiling process, you only have 1 degree of freedom. When you take a pot of water and you set it on the stove, you have already used up your degree of freedom. You have specified atmospheric pressure. Okay? Now you put a top on that and pressurize it, now you get a different boiling temperature. Okay? But once you specified one thing, everything else is fixed. What has already been specified here? Volume, more importantly, specific volumes. Specific volume is as much a property as is temperature or pressure. So once it's specified, that's it. We don't get to specify anything else. And if we want to change the relative amounts, then something else has to change. Anyway, so basically what we're saying here is we're adding energy. As we add energy, but we hold the specific volume constant, then all the other properties have to move along as the energy changes. The temperature has to change, the pressure has to change, the internal energy has to change, okay? Which is really what's driving it. All the entropy has to change. Okay, so all these things change because we are changing one property, and we've already used up our get out of jail free card. So we have to pay for this. Okay? So let's find out what the specific volume is. Now let me ask you a question before we do that. Will the specific volume in state 2 be more than, less than, or equal to the specific volume in state 1? It has to be. The volume can't change, the mass can't change, so it's just the volume, 1.8 cubic meters per 15 kilograms. Whatever that number comes out to be, that's the specific volume. 0.12?
Yeah.
0.12? Okay, thank you.
I was wanting to just say something,
Yeah, please.
because I struggle with this problem. Wait, that click.
Yeah.
I rephrased the question and then it became real easy. It was, find the specific volume of 15 kilograms of water vapor such that the mass occupies 1.8 cubic meters.
That's a good way of saying it.
You know, you take the vapor and you find this, that vapor's occupying 1.8 cubic meters or 15 kilograms of it. So you just have to match them up. You're gonna get a specific volume, you go to your table and look up that specific volume.
Let me rephrase what you're saying a little bit slower. In state 2, the quality is 100%. Therefore, the specific volume in state 2 must be VG. But the specific volume has to be the same as it was in state 1. So like you were saying, all you really need to do is take this, look for a VG of 0.12, and you found the state. Does that make sense? You can read off the temperature, you can read off the pressure, anything you want to know, you're done with that.
I had all kinds of trouble. I was looking to throw.
So pretty much I had the problem done, I just didn't look exactly, but all the answers are right, so it's good.
Well, part of the, you
Because I
know,
had all of that.
working this is good, it's good to know that this is the property of interest. However, making the leap that then is the
Yeah,
specific
that's where I
volume,
was stuck.
that's the key.
That's where I was stuck at.
That's kind of what I did, but I used these to give me the numbers at the end of it.
Use these numbers? Okay. As long as you've got that understanding, that's really what I'm looking for.
I was thinking, oh, God.
That makes sense.
Now, let me ask you another question. Could you find how much mass is in the liquid phase and how much mass is in the gas phase? Is that possible?
You talking about before?
Yeah, it's
Same
same.
ones. She's the qualification, I guess.
Okay, so what's the quality equation? What does it look like?
Quality is mass of vapor over mass of oil, is also equal to.
That's just the definition.
It's also V average minus V liquid over the liquid.
Like that? Good, that's right. That's the equation. Now, what would we plug in here? Well, VF and VG, we'll have to look them up. Where would we find it? In the back of the book. Which one? Because there's a bunch of them in the back of the book.
The one in
Degrees. Right, exactly. What about this V average? That's the point.
Yeah,
Because this is the overall, right? This takes the whole system into account. That's why it's V average. Once you do this, then you get the quality.
Anytime I calculate specific volume, then that's, I pretty much could say that I always calculating the average specific volume.
If you take total volume over total mass, you are always calculating average specific volume. That's right. But there is not one drop of liquid, nor is there one bubble of vapor that has that specific volume. Not one.
That's just
That's
this.
just the evidence in the whole. Once you wrap your head around this and you understand it, it's actually really simple. But until you do that, it seems so confusing. What's going on here? Anything else on the homework? Trust me, I struggle with all of this terminology. Anything else? Well, I don't recall where we were in the slides. Is chapter 4 not over? Yeah, I don't think chapter 4 is over.
I think we just got to like the bread and water.
Okay, so we're talking about heat capacities?
Yeah, that sounds real familiar. You said we were at a point where we could work with the next problem. That's that.
Okay, all right. So we talked a little bit about heat capacity and what it is, right? And so we can work another problem. While Blackboard's coming up with my slides, I will work the next one. This is an example problem from chapter 4. It's problem number 92. It deals with heat capacity. Now, did we talk about the heat capacities of gases versus the heat capacities of solids and liquids?
Briefly.
Briefly? Okay. Well, the heat capacities of a gas depend on whether you are adding energy or removing energy from the gas, either one, at constant pressure or at constant temperature, because the amount of energy you have to add to get the fluid, the gas, to change its temperature by 1 degree depends on whether you're adding it at constant pressure or temperature. Okay? So it makes a difference. If you add energy to a gas at constant pressure, that gas is going to expand. In doing that, the gas is going to push the atmosphere out of the way, doing boundary work against the atmosphere. And so the energy you're putting into the gas has to not only go in to increase the temperature, the internal energy of the gas, but it also has to push that piston out. Does that make sense? That's why it takes more energy to increase the temperature of a gas at constant pressure than at constant temperature. I'm still waiting. All right. Okay, now for a solid or liquid, when you add thermal energy to it, its volume doesn't change much. Now it does change a little bit, but not much, right? So if you increase the temperature of a solid or liquid, it doesn't have to push the atmosphere out of the way much. So it doesn't really matter if you add energy to that solid or liquid at constant pressure or at constant volume, because you will get the same amount of energy added to change by 1 degree. So problem number 92 deals with the heat capacity of a brass plate that measures 2 feet by 2 feet. Problem number 92 is on page 204. And I'll read it to you quickly. In a production facility, 1.2 inch thick, 2 by 2 square, well, 4 square foot, square brass plates with a given density there and heat capacity that are initially at a uniform temperature of 75 degrees Fahrenheit are heated by passing them through an oven at 1300 degrees Fahrenheit at a rate of 300 per minute. If the plates remain in the oven until their average temperature rises to 1000 degrees Fahrenheit, determine the rate of heat transfer to the plates in the furnace. So what we have here, basically what we have here is a very large mass flow rate where we have to increase the temperature of these solid masses. So here's a brass plate, 2 foot by 2 foot, density 532.5 pounds mass per cubic foot. Heat capacity 0.091 BTUs per pound mass per degree Fahrenheit. The temperature far away from the plate, you might remember this terminology from 220 when we talked about the surrounding gas temperature. The temperature far away, so that's not affected by the plate, is 1300 degrees Fahrenheit. And that, for some reason, no, there it is. I thought it wasn't in the text, but it is. It's on the figure and it's in the text. The initial temperature of the plates, T naught, is 75 degrees Fahrenheit, and the final temperature, TF, is 1000 degrees Fahrenheit. The flow rate, if you will, I'll just use the symbol F, is 300 plates per minute. Okay. We're supposed to find the heat flow rate. Well, this is a perfect application of heat capacity, because heat capacity tells you how much energy you have to add to get a substance to change its temperature by 1 degree. It turns out that they gave us the heat capacity. It's 0.091 BTUs per pound per degree Fahrenheit. So how many degrees Fahrenheit do I want to increase this temperature? Almost 1,000, right? It's 945 degrees. Okay, that's how many degrees I want to increase it. So I'll have to multiply this by 925. How many pounds do I want to increase? Well, I've got to decide that. I'll have to figure out really what the mass flow rate is. And what I'll get from that ultimately is a heat flow rate. Let me start off this way. The heat flow rate in the furnace would be equal to the mass flow rate of plates through the furnace multiplied by little q, where little q is the amount of heat I have to add to 1 pound of brass. Make sense so far? So if I know the mass flow rate, how many pounds of brass per minute are flowing through the oven, and I know how much energy I have to add per pound, that would tell me the total heat flow rate. Why would you care? Well, you got to pay for this. It would probably be a good idea to know how big it is, just like you have to put fuel in your car. It's nice to know how many miles per gallon your car is going to get, so you can figure out what it's going to cost to drive your car. All right, so let's work on this. In fact, if I expand this a little bit, the mass flow rate could be written as the flow rate of plates times the density times the volume of a plate times Q. Now let's back up and look at this just a little bit. If I look at the volume, this will be the volume per plate. Okay? So this will be cubic feet. What is mass per volume times volume? Mass. Right? In other words, this bit here would be the mass per plate. Does that make sense? This is just the amount of mass in one plate. And this number tells me how many plates per minute. So essentially, this bit here, F rho V, is the mass flow rate. This is the number of plates per minute times the amount of mass per plate, so it will give me the mass flow rate. All right. Now, to do this, we need to calculate a few things. The volume is pretty trivial. I forgot to give you the thickness of the plate that's in the problem statement. It's 1.2 inches, which we will have to convert to feet. I'm not going to bore you with all the details. It comes up to 0.4 cubic feet per plate. Once you convert the 1.2 inches to feet, then multiply 1 feet. Okay, so 2 times 2 times 1.2 converted. The density of the plate was given, or the material was given, so that takes care of rho. We have V. The flow rate was given, so we can actually get a number for the mass flow rate. Okay, so doing that, 300 plates per minute multiplied by 532.5 pound mass per cubic foot, okay? And that is the density multiplied by 0.4 cubic feet per plate. You can see cubic feet go away, plates go away, and we have pounds mass per minute, which is a mass flow rate. So that's the first 3 terms. And then I need you to remember to multiply by Q. So this comes out, once you put all these numbers together, to 63,900 pounds mass per minute times Q. You already see that this is going to be a huge heat flow rate. This is a heck of a mass flow rate. I mean, think about it. A ton would be 2,000 of these pound mass, all right? Would weigh, 2,000 of these pound mass would weigh a ton. So if you have 60,000 plus about 2 tons there, 60 divided by 2 would be 30, so that's about 32 tons per minute of brass. Would you like to have 1 minute's worth of brass and sell it to the scrapyard? I'd love to. I get quite a chunk of change from that, okay? So this is a heck of a mass flow rate. This is very unreasonable, but anyway. Now, so the question becomes, how much heat is required in order to raise the temperature of a pound of brass by 925 degrees? Well, that's easy. Little q would be Cp delta T. Right? In other words, take the heat capacity of 0.091 BTUs per pound mass per degree Fahrenheit, multiply it by the 925 degree Fahrenheit. Everybody understands where that's where I got that, right? 1,000 less 75, so 925 degree Fahrenheit temperature change, and you see how many BTUs per pound mass are required. In fact, it turns out that number is 84.175 BTUs per pound mass. Now, buying 1 BTU is extremely cheap. BTU of energy is pretty small. Okay, so 84 BTUs per pound, that's pretty darn cheap. But when we multiply this out, 63,900 pound mass per minute multiplied by 84.175 BTUs per pound mass, well, now we've got a heck of a flow rate, a heck of a power flow rate. This is, I'm sorry? Yeah, that's just BTUs per minute, so this is 5.378 E6 BTUs per minute. Now, that in itself, honestly, is not that large of a mass flow rate, or a heat flow rate, except it is per minute. That many BTUs you could buy over a day's time, it wouldn't be too bad. If you buy that every minute, it's gonna be really, really expensive. In fact, I performed a conversion. What I did is I took the 5.378 E6 BTUs per minute, I multiplied it by 60 minutes per 1 hour, and then 1 kilowatt per 3412.14 BTUs per hour, which is also known as BTUH. So BTUs per hour go away. And we find that we need a heat flow rate, Q dot, of 94,568 kilowatts. We need 95 megawatts approximately to get this thing to go.
So little Q, I'm sorry, little Q is always CPWT.
Not necessarily, but in this case it is. It's just the amount of heat flow rate per mass in the system.
I mean, it's
I
nice.
said it's kilowatts versus, maybe a little less
Kilowatts.
as your factor or something.
What's that?
Maybe a little less as your gen
I
factor.
don't know where you get 7 cents a kilowatt, 'cause it's not that around here.
Well,
You know, like-
10 cents per kilowatt hour is the price. You don't pay for power.
Right.
You don't pay for kilowatts, you pay for energy, which is kilowatt hours. So if we let this thing run for 24 hours, let's figure out a cost. Let's just say that we could buy electricity and use it directly to heat up these places with no loss, okay? So in your calculators, take 94,568 kilowatts, and this is a big process, so let's assume it's gonna run for 24 hours a day. So multiply that number by 24, you'll get kilowatt hours. And around here, it's anywhere from 10 to 11 cents per kilowatt hour.
69,632.
So take whatever you got after multiplying that by 24 and divide by 10, or multiply by 0.1, which is $0.1 per kilowatt hour. How much money are we talking about?
2.27 E5.
250,000.
$50,000 a day in heat.
Few dollars.
See, but it's all fine and dandy seeing this, I mean,
Thank God that process has zero, it's perfect efficiency.
Yeah, no such thing. What's that now?
it's just, I mean, seeing you do it on the board like that is all fine and dandy. When I get it home,
Right.
it won't be so fine or dandy.
That's what getting homework and homework's all about. The key here is understanding what all this stuff
I
is.
mean, I understood the mass flow rate, and I understood the individual parts. It's whenever I go to put it all together, you know.
I understand that.
So what's your kilowatt BTU conversion?
It's just 1 kilowatt per 3412 BTU hour. It's just a conversion factor in front of your book.
I'm like Norm, my problem isn't following along with it right now. It's looking at the stuff and saying, oh, this is what I have. What about, and how do I organize this to get what I need to where I, so I get where I'm going?
Sometimes I work the problem forward, where I just write down an equation, and I say, this is what I want, I gotta get these two things to get this, and I just plug through it straightforward. Sometimes I work the problem where I'll start collecting pieces of information, try to put them together, and build it up from the bottom. Because you can work the problems two ways. Most of the time, you guys will be working from the bottom up.
Right.
This is a top-down approach, and so it looks more difficult than probably it would be if you tried it. Because you'd be putting little pieces together, you'd see this flow rate, you'd say, plates per minute. Well, I don't know, but I can figure out the volume of this thing, so I'll go do it. Well, if I got volume, I see density, I can figure out how many pounds is in a plate. Well, wait a second, if I got so many plates per minute, I can figure out how many pounds per minute is flowing through this thing. That's a mass flow rate, and something that I think.
There's nowhere in the chapter that I've seen so far that tells me CPWT equals little q.
Well, that's because all we're saying, let me.
Okay, there it is. No, we're good. As long as I can go back and start at the chapter or in my notes.
Well, let me ask it to you this way. Let's say that the process, instead of being in a furnace where the surrounding air temperature is 1300, let's say, just for the sake of argument, I don't know, brass is probably a pretty good conductor, so getting an induction heater to heat up brass might be difficult. But just for the sake of argument, let's say it was a steel plate instead. Different numbers, but the same idea. Okay? And you're heating it up via an induction heater, which is basically just a coil of big copper wire you put around a part. You pass a big current through it that induces current into the plate itself. The plate is resistive, and so it heats up. You can actually heat treat stuff this way. You heat it up where it glows red very quickly, drop it into some kind of bath, heat treat it. Go. Okay, so that is actually a way of doing it that's very efficient, because all of the energy essentially that you're putting into the coil goes into the plate.
Goes into that where it belongs.
Right, exactly. Now, why did I go down that road? You said something. Oh, yeah, so basically what's happening here, you're not transferring heat into the plate anymore. Right? You're not transferring energy due to a temperature difference. You're transferring energy directly into the plate. So then what's happening? What's really happening is the internal energy, the thermal energy of the plate is going up. And really the equation should be delta U equals mCp delta T. Okay? Or maybe delta little u equals Cp delta T. And the only reason that this works with Cp, usually Cv goes with delta U. But for a solid or a liquid, it doesn't matter if it's Cv or Cp, it's essentially the same thing. Okay? Because the difference between a change in internal energy and a change of enthalpy in this solid or liquid is the same thing. And this will be about the same as delta H, because the plate's not going to expand. So there's not really any boundary work to be considered here. So anyway, this is really the equation. So how do we get the energy of the plate to increase? Well, we could do it by adding heat, and that's why this is little q. Okay? Because what we realize is Q is just a way of making a deposit of energy into the plate. And quantifying the way that that plate responds with temperature is heat capacity delta T. Okay. We could transfer it in via work, like I suggested with the induction heating. Okay. Does that confuse you more or help any? Well, if you're falling asleep, why don't we go outside, set some paper on fire?
Yeah.
And then I'll go print off the other exams that are missing. And then we'll come back and work it for about 30 more minutes and then take our quizam.
Let's study